This is tutorial 6A, question 0A. This question asks us to analyze the synthesis equation of the DTFS for n equals to 16. This means that we are given x, a periodic signal that repeats every 16 samples. We then use the synthesis equation to reconstruct xn. This is the DTFS synthesis equation. You will notice that the small letter n will go from 0 to 15. The C case will also go from k equals to 0 to 15. This big N is 16, and this letter n is the same as this letter n here. Whatever we put for letter n, we're going to put for small letter n here, which is 0 to 15. And then you might be wondering, if we are going to put n equals to 16 to 31, then what happened? Then similarly, here we will put n equals to 16 to 31. And it doesn't matter, because whatever n you put, it is the same n here. Now, because xn is periodic, whether you are generating for n equals to 0 to 15 or 16 to 31, or even n equals to minus 16 to minus 1, they would be all this periodic sequence. It does not really matter, and in fact, for our purpose, we typically only generate for this particular range, which is n equals to 0 to 15, or I should just say capital N minus 1. The purpose of this question is to show that the DTFS equation can be written into the vector matrix notation, where this is the vector of x from x equals to 0, 1 until 15. And this x actually is a linear combination of b0, b1, b2 up to b15 that is weighted by these coefficients. And I should write c15 here. When we view DTFS synthesis equation like this, then this brings us to visualization of Fourier transform from the linear algebra perspective. And it is actually very rewarding to view Fourier transform as such. Then these column vectors are the basis for the space C n. While x is Rn, n equals to 16, the basis actually is a complex vector with 16 elements. You may be wondering, how can I add column vectors of complex vectors and I end up with real? And the answer is that the coefficients, there will be complex conjugate of each other, and the imaginary part will cancel later on. So now let's answer the first question, which is, what are the purposes and characteristics of CK and BK? So CKs, C0, C1, C2s are called the Fourier coefficients. They are complex number, and their purpose is to multiply, meaning scale the vectors BK, and introduce phase into the vector BK. What do I mean? Well, let's try this. If C0 is a value of 3, then 3 multiplied by all this 1, these vectors will become all 3s. What about introducing 3 here? If we have 3, this is 3, the first one will be 3, the second one will be 3 ei 2 pi over, in this example, 16. And this guy, still 16, but because here is for So what we do is that we are introducing a gain for this vector. Now, if C1 has a magnitude and theta, then what will happen is that the first guy will become C1 theta. And here will be C1 EI 2 pi over 16 plus theta. So what we are doing is that we can multiply a constant with a phase, and we would scale this complex value by that constant, and we introduce the phase here. So the purposes of C0, C1 up to C15 is to scale and introduce phase shift onto the B case. From the synthesis point of view, what we can now think of the C's as how much contribution of different vectors will contribute towards constructing X. So for example, if C0 is a very large value, then we know that this vector X is very near or very similar looking to this constant 1 times this scale. So this is the purpose, which is the Fourier decomposition of a vector into these complex exponentials. And the C's will tell us how much, as in the scale, and the phase shift that will be needed for each different frequencies. Why do I say it's frequency? Because B0 is actually a frequency of 0 radian per sample. B1 is actually at every step, you see, we are rotating anti-clockwise by 2 pi over 16 sample. See, this first guy has no phase. This is 1 angle 0. The second guy is 1 angle this phase. This phase is 2 pi over, in this example, 16. 2 pi over 16, I calculated it as 2 pi over 16 equals to pi over 8 radian per sample, which is 22.5 degrees per sample. In 16 steps, we will rotate by 360 degrees. So here, from the first sample to the last sample, we are rotating 360 degrees when we hit the 16th sample. So X16, sorry, or B116 here, this value here will be 1 again. So this completes the discussion of question 0A, part A. You can see more of my discussion of this idea in slide 6.1.3 at page 8, as well as page 9, where we visualize the B's in terms of the arrows like this. And in here, the arrows basically shows the position of the phasor. And you will see that for B0, from sample n equals to 0 to 7, the phasors does not change, because we are talking about B0 means there is no change of frequency. The frequency is 0 radian per sample. So the phasor remains constant from sample 0 to 7. What about B1? B1 means 2 pi over 8 here. At every sample, we will rotate by 2 pi over 8, which is 45 degrees. So in one step, we'll rotate by 45 degrees, second 45 degrees. So compare this to here. The arrow is first here, which means that the arrow is here. The second step, the arrow is here. The third step, the arrow is here. The fourth step, the arrow is here. The fifth step, arrow is here, and so on. So can you see? I draw the arrows as well to show the positions of the arrows, the phasors, as it goes from sample 0 to sample 7. Why is there a circle? The circle is the unit circle. It shows the radius 1, and we are actually having a rotating phasor of radius 1, because it is 1 ej omega n. Now, in our questions, we are asking for n equals to 16, so you should see n equals to 0 up to 16 here, and k will be 0 up to 16. So I should draw a big picture. I'll show what it looks like now. So this is the picture for n equals to 16. Here is n equals to 0, n equals to 1, up to n equals to 15 here. This is B0, this is B1, and B2. Let's examine the arrows showing the phasor position as n equals to 0 goes to 15. For B0, remember that the frequency is 0, so nothing changes. What about B1? B1 will produce one step, and it needs 16 steps before it completes one cycle. So it goes 1 step, 2 steps, 3 steps, 4 steps, and so on. And it is rotating anti-clockwise, as you see now. And finally, at the 15th step, it is 1 step away to going back here again. What about B2? B2 starts again at the same place as everybody else, but in 1 step. Can you see? In 1 step, he is the same as the 2-step guys of B1. The reason is B2 is rotating twice faster than B1. B3 is rotating 3 times faster than B1. So you look at the first one is always the same. The second one is the 3 times faster. So now you can appreciate this diagram, and you can go into this MATLAB to run this plotting by changing various n. So with this, we end question 0a, part small a. Thank you.